Kia ora and welcome to this video on question 5 of the 2019 School Calc exam. Whilst there's only two parts to this question, they're pretty intense. The first complex numbers question we're going to look at in two different ways. We're going to solve it algebraically and also look at a geometric proof. And then part B involves a typical misconception that students have regarding ellipse. So we're going to look a little bit more into that, and I'm going to show you a diagram that helps us understand the solution a little bit better. Okay, so question 5a. A typical answer to this would involve just substituting cos theta plus I sine theta into the expression. And it's similar to excellence problems where you have to sub z equals x plus iy in. So if we substitute cos theta plus I sine theta in for w, the first thing we have is two complex numbers that are divided, and neither of the numerator or denominator are in a standard form. So we put the real parts together and leave the imaginary parts separate. And when you're in polar form, addition and subtraction is just messy because the numerator and denominator are no longer in polar form. They're in x plus iy form. And if we wanted it back in polar form in some r cis theta, we'd need a bit of trig to do that. It's not nice. To get it into a standard format though, we need to use the conjugate of the denominator times by that will ensure that the denominator goes to a real number. Okay, and when we times out these things, we're just going to be clever in how we do it so that it doesn't get too messy. The denominator first, the imaginary stuff should cancel, so we get the real part times the real part. Cos theta plus 1 all squared. And we get I sine theta times negative I sine theta, which is plus sine squared theta. Up the top there's four terms when we expand the first one and the first one, so cos theta minus 1 and cos theta plus 1. That's going to give us a real number. And the last terms, I sine theta and minus I sine theta, they'll give us a real number, plus sine squared. And then the other terms are imaginary. So I times sine theta cos theta plus 1 and minus sine times cos theta minus 1. Okay, the numerator, when we expand it out, we get cos squared theta minus cos plus cos minus 1 plus sine squared. Cos squared plus sine squared equals 1, which is brilliant because those things all cancel, 1 minus 1. And the thing we're trying to aim for is a purely imaginary number. There's no real part there. I times tan theta over 2 doesn't have a real part. So the fact that we've got this whole term here cancelling is exactly what we wanted. Plus I times by 2 sine theta. The sine cos cancels with the minus sine cos. Denominator, expanding it out, I've got cos squared and sine squared makes 1, with the other one makes 2. 2 plus 2 cos theta. Put some equal signs in. Okay, that equals I times by, we can divide out the 2's. So we get sine theta over 1 plus cos theta, and it looks like you're wrong, you know, like you're aiming for tan theta over 2, and we've got this expression here. If you're ever unsure about something in an identity and you think you're wrong, just type in the function that you have. So sine theta divided by 1 plus cos theta. Oh, it looks like a tan graph, so we're probably right. And then we type in tan of x over 2. And you could use your graphics calculator to do this if you felt that your identity that you were trying to prove had like a little error in it, but because these functions are the same, it gives us confidence that we've got the right expression, we haven't made any mistakes. For this last step, what we need is to turn the angles thetas into half angles. Okay, we're looking for tan of theta over 2, which is a half angle. So to do that, we use the double angle formula. Okay, the double angle formula for sine is sine 2 theta is 2 sine theta cos theta. And the only difference here is we don't want 2 theta, we just want theta. And so I've halved that angle, I need to also halve the other angles. The other formula that we want is a 1 plus cos theta. If I look at the double angle formulas, I've got 3 options. I choose the one which is 1 plus cos 2 theta equals 2 cos squared theta. Okay, that's got the cos theta plus 1 in it. Again, I only want half of that angle, I don't want 2 theta. So I get rid of the 2 theta and make it theta, meaning I have to half the angle on the right hand side as well. Okay, and then I substitute these new identities in. 2 sine theta over 2 cos theta over 2 and 2 cos squared theta over 2. The 2's cancel, the cos theta over 2's cancel, one of them does, and we're left with sine theta over 2 divided by cos theta over 2, which is I times tan theta over 2, because sine over cos is tan. Brilliant. So that's the algebraic proof of it. Now let's have a look at the geometry and how you could do this using a geometric proof. Okay, I've prepared this earlier because it was a bit of a mess. But the first thing is in the problem, it tells us that the complex number w is somewhere on the unit circle because we know it's equal to cos theta plus I sine theta. That's 1 cis theta. So if we pick any random complex number on the circle, okay, it uses z instead of w, but don't worry. Z plus 1 is to add the real number 1 to z. You're just going to move it to the right by 1. Not up or down. Z minus 1 goes to the left by 1. And look, I can move the z and it still stays 1 to the right and 1 to the left. Now, what we've done there, because z is 1 away from the origin, it has a modulus of 1 to start with, we've actually got another circle here. Z plus 1 and z minus 1 are 1 away from z, and z is 1 away from the origin. So those 3 points there are on a circle that goes through the origin, and it has a radius of 1. The complex number z, if you look at z, it has a modulus of 1, it has an argument of theta. Z plus 1 actually has an argument of theta over 2. What we've got there is an isosceles triangle, and the base angles are the same. And that's enough to prove that the line from the origin to z plus 1 bisects the argument of z. So the argument of z plus 1 is theta over 2. Okay, if I hide that one, bring up that one, because we've got a circle and z minus 1 and z plus 1 form a diameter, we have a 90-degree angle at the circumference. That's a year 11 geometry rule. Geometric reasoning, angle at the circumference inside a semicircle is 90 degrees always. And that's enough to prove this geometrically. So if you could just remember that picture, and if you need to go back and look at it, you do so. But what we've got in this question was w minus 1 over w plus 1. Now these are two complex numbers in themselves. Let's call it r1 cis theta 1 over r2 cis theta 2. It actually doesn't matter what the moduli or the arguments are, but when we divide in polar form, we divide the moduli and we subtract the angles. So r1 over r2, we've got to work out what that quantity is. We don't need r1 or r2 individually, but we need the fraction. and then we need the angle between them. Okay, let's see. R1 over R2 is the modulus of z minus 1 divided by the modulus of z plus 1, which is the tan of the angle theta over 2. Okay, because that acute angle in that right angle triangle, the smallest one, the top right, is theta over 2, and the tan of that gives us the fraction. And then the theta 1 minus theta 2 is the difference between the arguments, which is 90 degrees. So this equals tan of theta over 2, and then cis of 90 degrees, which we know is I. So we get I times tan theta over 2. How cool. Alrighty, part B. Okay, we've got an ellipse. We're told when we write an ellipse in parametric form that theta is not the same as the angle at the origin, although it's often mistaken for this. I remember making this mistake in an internal assessment many years ago. But the two angles are closely related, and they are the same at the x-intercepts and y-intercepts. Now, just on a side note, if we had a circle, terrible circle, and I had this point here, xy, the equation of the circle is x squared plus y squared equals r squared. Radius is r. Let's call this angle theta, the anti-clockwise angle. Then a bit of trigonometry tells us that this length is r sine theta and this length is r cos theta. So in other words, y is equal to r sine theta and x is equal to r cos theta. And in that case, the parameter theta is the anti-clockwise angle. So it works for circles, but it doesn't work for ellipse. And let's just have a look at this picture. Another picture that I've created in advance. Let's go out of here. Where is it? This one. Okay, so I've got a random ellipse just drawn here, and A and B can be anything, so let's just, that will do. Now, this point A, which is moving around the ellipse, if I want to find the coordinates of A, at that point, theta is 0.66. So if I put 0.66 into the equation, A cos theta, B sin theta, I will get the coordinates of A. But theta equals 0.66 is not there, the anti-clockwise angle. You can see I've written that in as phi equals 0.54. So they're not the same. But at the intercepts, A has that's theta equals 0, also an anti-clockwise angle of 0. Up the top there, that there is when theta is pi over 2, also when phi is pi over 2. So there are obviously points where it is the same, but in general it's not. Okay, so what we've got is we need to find the biggest difference between theta and phi. But first up, they ask us to write an equation that relates them together. And that's actually quite an easy equation to do, because we do the same thing as what I showed you with circle. We drop that line down there and make a right angle triangle. This height is b sine theta, because it's the y value. This is a cos theta. And therefore we have tan of phi, opposite over adjacent, b sine theta over a cos theta, which is b over a tan theta. So that's our equation that connects the two things together. Tan of phi is b over a tan of theta. Okay, the next question asks us what values of phi is the difference between the angles the greatest. So let's call this difference, we'll call the difference y, and we'll call it theta minus phi. Now I want to differentiate this but that would involve me going y is equal to theta minus the tan inverse of b over a tan theta. Now, I'm going to do this, but I'm going to also show you a way that it doesn't need this next bit of knowledge. So just on a side note, if I want to differentiate this with respect to theta, theta is the only variable in this equation, b and a are constant, I need to know the derivative of tan inverse. So on a side note, if I just go, let u equal the tan inverse of x, then the tan of u is equal to x. And if I differentiate this implicitly, or if I go dx du, actually is the better way of doing it, the derivative of x with respect to u is sec squared u, and then I flip it upside down, du dx is 1 over sec squared u. That's the derivative of the arctan function. Make a triangle, hopefully with straight sides. Close enough. Tan u is opposite over adjacent, so if I call that angle u, opposite x adjacent 1, this is 1 plus x squared square rooted, and sec squared, the reciprocal of sec squared is cos squared, and cos in this diagram is adjacent over hypotenuse, and I want to square it, so I get 1 over 1 plus x squared. So the derivative of the inverse tan function, or arctan function, is 1 over 1 plus x squared. And I've memorised that because I've used it heaps over my time at uni and teaching. So if you want to memorise that, then I can solve this problem using it. Okay, dy d theta equals 1 minus 1 over the stuff squared plus 1. Okay, because it's tan inverse of something, so it will differentiate to 1 over the something squared plus 1 times by the derivative of the something, because we need the chain rule, and we'll make that equal 0. Okay, how do we solve this? We move that whole term to the other side, so it's 1 equals b over a sec squared theta divided by b over a tan theta all squared plus 1, cross multiply, now we need to use a trig identity, expanding this out, b squared over a squared tan squared theta plus 1 equals b over a, and sec squared is equal to 1 plus tan squared. So I've got oh, is this even nice? This doesn't look very nice. Just going to have a check to see if I'm on the right track with this. It's supposed to come out as a quite nice answer. Oh, of course the marking schedule didn't do it this way. So sec squared, 1 plus tan squared. I've got a 1 there, so it's supposed to be there. Yep. Okay, so I've got b squared over a squared minus b over a, all times tan squared theta, equals b over a minus 1. Just rearranging that. Now if I put the fractions together on the left hand side, I've got b squared minus ab over a squared, and then on this right hand side I've got ab minus a squared all over a squared. Cancel the a squareds. tan squared theta. This was supposed to be the easy way of doing it. Okay, that factors a times b minus a over b times b minus a. Brilliant. Okay, it did actually simplify quite nicely. So tan theta is equal to plus or minus root a over b. And from that we can find tan phi, because the question does ask about phi. It turns out that this is plus or minus root b over a. So phi is the inverse tan, plus or minus root b over a. To find that last relationship, to find the phi one, we just go back to this relationship here, and we replace the tan theta with the expression we found. Okay, so that there involves differentiating using the arctan function, which you might not have known. So how do you do that in a different way? Let's get rid of all this. So, okay, method 2. When we had the theta minus phi expression, which was our y equals, we want to find the biggest, or where the biggest difference is. So we want to differentiate y. But if we tan both sides, and think about what the tan graph looks like. The tan graph looks like that, and there's an asymptote at pi over 2, or 90 degrees. If we say that this is our theta minus phi on this axis, the biggest value of it will also occur at the biggest value of the tan of it, because the theta minus phi is never going to be bigger than 90 degrees, and this tan graph increases up to 90 degrees. So that tan of theta minus phi is going to be biggest. The biggest value of theta minus phi will generate the biggest value of tan of theta minus phi. In other words, I just need to differentiate the tan of y. There's a chopper going in overhead. Okay, so using the compound angle formula for this, tan theta minus tan phi over 1 minus tan theta tan phi. The reason that this compound angle formula is useful for us is because we already know how tan phi and tan theta relate. So I can eliminate one of the variables by just substituting that relationship in. Actually, let's sub in the tan phi one. So tan theta is a over b tan phi and I'm going to call this this tan y, I don't know, just call it s, because we want the biggest value of s. So ds d phi, the only variable left is phi. Use the quotient rule, so diff the top, a over b sec squared phi. Actually, let's tidy it up first, because that's going to be a mess otherwise. A over b minus 1 all times tan phi. Okay, so the derivative of the top is a over b minus 1 sec squared phi. Did I say phi? I meant phi. Times the denominator. Minus the derivative of the denominator. The 1 disappears. We've got tan phi all squared, so we bring the 2 down, minus 2a over b tan phi to the power of 1 times the derivative of tan phi times the numerator. So the other way was definitely the easiest. All divided by the denominator squared. The This is the last question in the exam though, so it usually is the harder one. Okay, we want that equal to 0 because we're looking for the biggest value of s, biggest value of tan of the difference. Okay, fortunately we can cancel out a whole heap of stuff here. We can divide out that factor in both of the terms because a over b is not equal to 1. If a over b equaled 1, that would mean that, so if a over b equaled 1, we'd get tan theta is equal to tan phi. But we know that theta doesn't equal phi because that would be the minimum. That would be when there's a difference of 0. So we can rule that out. You know, when we differentiate and we make it equal 0, we get mins and max. We don't want that. That's a min. Sec squared theta is never equal to 0. So we say a over b doesn't equal 1. Sec squared phi doesn't equal 0. Never equals 0. So that leaves us with a little bit left to solve. 1 minus a over b tan squared phi equals 2a over b tan squared phi. So be careful there, there's a tan phi there, there's also another tan phi that we haven't dealt with. Okay, and rearranging this. Oh, is there a mistake? Oh my goodness, my compound angle formula. That should be a plus. That's a plus. That's a plus. That's a plus. That's a plus, but oh no, but the quotient rule, oops, says I'd actually differentiated wrong. The quotient rule has a minus in the numerator, so that's good. That's a plus. Okay. So that's a plus, and that's a minus. No, it's a plus. Oh my goodness. Okay, one little mistake could have led to the whole thing being wrong. Okay, we've got like terms, so move one to the other side. A over b tan squared phi times by b divided by a. Tan squared phi equals b over a. Tan of phi equals plus or minus root b over a, which is the same as phi equals tan inverse plus or minus root b over a. Okay, what does that actually mean? Let's go back to that GeoGebra diagram just to finish this video. At the moment, I've got A is 1.8 and B is 1.4. I've set it up so that I'm dealing with theta. I'm sliding theta. So rather than inverse tan of root b over a, I want inverse tan of root a over b. And if I work that out, down the bottom there it says 0.85. That's saying when theta is 0.85, we have the biggest difference between theta and phi. At the moment, we've got a difference of 0.13. If I slide theta smaller, the difference decreases to it's 0.12 at the moment, keeps going down 0.1 and so on. If I go the other way, it goes bigger, so it goes smaller. So that formula is telling us that we're in the right spot. When it's 0.85, it's the biggest difference. Although there isn't much of a difference either side of it because of the shape of my ellipse being so close to being a circle. But if I elongate, if I make it stretch it out a bit, now our biggest value is 1.03. Okay, so when theta is 1.03, okay, about there, the difference between theta and phi is actually quite big. It's 0.48. And then either side of that, we get smaller differences. Alrighty, hopefully you found that useful. Catch you in the next one.